Okay. Hey guys, this is the first video for this homework assignment, tutorial 4. And for this assignment, I'm actually going to do this a little bit differently because of some aspects of this problem that I'll discuss later. But I'm going to be discussing problems 1 and 2 in this first video. And basically what I'm thinking of doing is just solving number 1 for you completely. Or not completely, I guess, but we'll go over almost everything in this one, and then I won't go over anything on number 2. So you guys can guess which one we'll obviously be grading then, right? So I'll go over number 1 in depth because I think there's some minor things that I can't really. These problems are simple enough that I can't really show anything without giving away the solution. Yet they're detailed enough that it warrants going over. So for number 1, and for number 1, 2, and 3, make sure that you get your reactions correct because you will be using those later. So really quickly, let's just do number 1, and you'll see that there's really not too much work for this homework set, right? So if I have number 1, this is my. I think it was something like this. If I look at this, I can tell right away by sum of forces in the x that my AX reaction will be equal to 0. I can use my sum of moments about A, and I will find that, let's say that this way is positive, then I will have, this is W, and this is 2L, so my load is W times 2L times 1/2 times the distance to the centroid, which is 2L times 1/3. I have this vertical reaction at Cy, so I have minus Cy times 2L equals 0. And if I solve this out, I should end up getting that that Cy is equal to WL on 3. Let me just double check that I have this correct here. I think this should be correct. And I should have that if I do my sum of forces in the y direction, I should get that AY is equal to 2WL on 3. So those are my reactions. As you can see, like that really didn't take too long there. So for my diagrams, let's draw this out again. So if I draw this, and instead of putting reactions there, I'll just put WL on 3. This was 0, and this was 2WL on 3. I can see right away that I'm going to have axial force in this member here because I have a vertical force and a vertical force. This will be in compression. I'm not going to have any axial force in here, right? Because if I do my little cut here, I don't have anything squeezing it from in the horizontal direction. Down here, I'm going to have no shear in here. I'll have no shear in here, but I'll have shear in this upper portion here. So really quick, let's just try sketching our diagrams. So I will draw 4 of my, and I really want you guys to get. I got a few emails about this, a few questions about this. I really want. For this class, it's really helpful if you draw your diagrams directly on your frames. So in other words, I'll call this one axial, this one shear, this one moment, so that my shear and moment are on top of each other, and this will be deflected shape. So for my axial force diagram, let's just try sketching this really quickly. I have 2WL on 3 in compression, right? Like the reaction the axial force is basically equal to this reaction. So if I say that this way is positive, I want to say that this is in compression. I'm going to go down, and I'm going to say that this is negative. And it's going to be negative 2WL on 3. And that is my axial force diagram. So as you can see, it's very straightforward. For my shear, I'm going to have something similar. Right, I keep telling people to follow your arrows here. if I look at this member, I have, and this is probably easier if I do it this way, my shear is going to be 0 here, right? I have a vertical force of 0 in this section, so therefore I have no shear. I'm not going to draw anything here. If I go back to the proper orientation, I have an upwards arrow down here. This basically gets translated all the way up. So my shear diagram, and let's say that this is my positive sign convention. I'm going to follow my arrows up, so I'm going to go up by 2WL on 3. And then I'm just going to, the slope of my shear diagram is equal to the value of my distributed load. I have a large downward distributed load, therefore my shear diagram is going to have a downward slope initially. Sorry, it should be, initially. I had to, I'm just going to follow this arrow down. I know that I have to end at negative WL on 3. So I know that I'm starting off at 2WL on 3, and I'm going to end at negative WL on 3. The idea is that at the very end, this force brings me back up to 0, so therefore I need to start off below, I need to end below 0. And then I just follow my arrows. So I start off with a steep slope, I end with a 0 slope, therefore my diagram is going to look something like this. Right, I start off with a steep slope here because I have a large value for my distributed load. My distributed load gets smaller and smaller and smaller, therefore my diagram, the slope of my shear diagram slowly changes until it becomes 0. This should end at 0 here. Now based on that, I can just go to my moment diagram. So for my moment diagram, I have no shear here. I have no applied moments here. Therefore my moment diagram is just going to be 0 here. And Professor probably mentioned this in class before, but he normally draws his moment diagrams upside down. So if my shear diagram is drawn this way, then my moment diagram will be drawn this way. Right? So this is opposite of this, and this is opposite of this. I have no moment in this arm, so I'm going to ignore that one. Up here, my moment diagram is going to, my moment diagram for a frame, as I go around the corner, it has to have the same value. So I started at 0 moment here because it's a pin. I have no shear in this section, therefore my change in moment is going to be 0. So I start off with 0 moment here. I have to end at 0 moment again at the very end. Therefore, if I'm looking at this section in here, what I'm going to see is that the slope of my moment diagram is the same as my shear, as the value of my shear diagram. I have a large positive value for my shear diagram, therefore I'm going to have a large positive slope. I have a large negative shear at the end of my diagram, I'm going to have a negative slope. Remember, this is positive slope because I have a downward arrow, a downward sign convention. This is a negative slope because I have a downward sign convention. And I'm going to have 0 slope somewhere down here. So somewhere here I'll have 0 slope. And I'll just connect it to like this. So the last thing you're asked to find is, last thing, you need to find the, you need to find this value, you need to find M max. M max is equal to the area under one of these two curves. Now this is going to sound a little bit strange, but we have formulas for parabolas to find the area under or above a parabola. For example, I could find this area very easily. But those formulas only work if we're looking at a portion of the parabola that starts off with a 0 slope. So if I look here, this slope ended at 0. Therefore, I can use my parabola equations for this area. I cannot use my parabola equations for this area because I don't have a portion in here that ends with a 0 slope. And that sounds a little bit, it sounds like a little bit like a cop-out or something, but like it just, if you look up the area formulas for a parabola, you'll and see how they're derived, you'll have a better understanding what I'm trying to say by 0 slope there. To find this length, all I really need to do is go back to my distributed load. So I know that my distributed load was something like this, right? I want to find the area of this triangle that exactly equals my reaction. To do that, I basically need to find, I need a general equation for the height of my triangle, the height of my distributed load. So I need to know what the height of my distributed load is at any given point on BC. And that might sound a little tricky, it's actually quite easy. I just use my slope-intercept form. So this is x. And I say, well, what is the slope of this line? The slope is just w on 2L. What is the y-intercept? The y-intercept is 0. Therefore, the equation for this line is just w of x equals w on 2Lx. This is the height of this triangle. X is the length of the base of the triangle. If I want to find out how the area of this triangle for any value x, I can just go back. If I'm gonna go down here now, and I'm just gonna say that this is w of x times 1/2. In other words, I'm going to have w 2Lx squared times 2, so this will be equal to wx squared on 4L. I set this equal to my reaction, right? By doing that, I find the location where my shear diagram crosses the 0, it becomes 0. So in other words, I said wx squared on 4L equal to WL on 3. If I solve for this, I should get that x is equal to 2L on root 3. And this is about 1.15 L. So this length is about 1.15 L. From there, I can get the area of this parabola. And that area is just, you can imagine that if I were to put a box in here, I would have a base and a height. The area of a parabola is just 2/3 base times height, or 1/3 base times height. And it's different, so this, you see how I have it's going over the diagonal here? It's taking up more than half the rectangle. That's when I would use 2/3. If I were interested in the other side, that's when I would use 1/3. In this case, I'm interested in the 2/3 portion. So I'm going to the equation for this is going to become, I'm interested in finding my m max. It's going to be equal to 2/3 base times height is equal to 2/3 times that 1.15 L times the height, which is just equal to the value of my reaction, right? Negative WL on 3. Sorry, let me ignore the sign here. And if I do all that, I should end up with this ended up becoming 4WL squared on 9 root 3, which is about equal to 0.256 WL squared. And I can plug that value in here. So that's about everything for problem 1. I'll sketch in the deflected shape. You only have bending where you have moment, and I'm running out of time on this video, so I'm going to have to cut this quickly, but you only have deflection where you have moment. You have no moment here, therefore this is going to be a straight line. You have bending here. Your deflected shape is going to behave similar to your moment diagram, so I should get bending that looks like this. This will be a right angle still. So that'll be my deflected shape. Okay, so that's just about everything for problem 1. If you have any questions on either this or problem 2, which is very similar, feel free to email one of us or stop by office hours.